You've probably ridden a train, but have you ever asked yourself one simple question? Where is the engine? Because with cars, it's obvious. The engine is in the front, but many modern UK trains don't have a big locomotive at the front at all. Yet they can still pull hundreds of passengers at high speed. So how does a UK train actually move? Where does the power come from? And why do some trains use overhead wires, while others use a third rail? Today I'll break down the UK train engine system in the simplest way possible. Electric trains, diesel trains, hybrid systems, and how the wheels get power. And by the end, you'll understand train engines better than 90% of passengers. Most people imagine trains like this, a giant engine at the front, and carriages behind it. That's how old steam trains and classic diesel locomotives worked. But the majority of passenger trains in the UK today don't work that way. Instead, most modern UK trains are powered in one of two ways. Electric power from overhead wires or a third rail diesel power. But here's the twist. Diesel trains usually don't drive the wheels directly. They often generate electricity first, and then electric motors turn the wheels. Or the real engine of a modern train isn't a big block in the front. The real engine is basically a power system plus electric motors spread across the train. Let's unpack it step by step. Visual. Old locomotive pulling coaches gives modern multiple unit train with power spread out. If you want to understand how a UK train engine works, just remember these four parts. The body where passengers sit, the bogies, the wheel frames under each carriage, the traction system, the motors that actually turn the wheels, the control plus braking system keeps everything safe and smooth. The most important part here is the bogie. A bogie contains wheels, suspension brakes, and sometimes a traction motor, the thing that provides the actual push. And this is the biggest surprise. Modern trains are moved by electric motors, not by a mechanical engine driving the wheels. Even many diesel trains use electric motors to move. Now let's focus on the real hero, the traction motor. Visual bogie diagram labeled gives motor highlighted gives wheels turn. A traction motor is basically an electric motor that turns the wheels in a car. Engine makes power, gearbox transfers power, driveshaft turns wheels in a modern UK train. Power comes from electricity. Electricity goes to traction motors. Motors turn the axles, wheels rotate, and the train moves. And trains use motors because electric motors give you massive torque from zero speed, smooth acceleration, efficient energy use, strong control over speed. That's why electric trains are usually faster, smoother, and cheaper to operate than diesel. But here comes the next question. Where does the electricity come from? Because UK trains are powered in two main electrical ways, overhead wires, third rail. Let's start with overhead wires. Visual car engine gives gearbox animation. Then train traction motor gives axle rotation animation. In many parts of the UK, electric trains use overhead wires. This system is called overhead line equipment, or OHL. The train collects electricity using something called a pantograph. That's the metal arm on top of the train that touches the wire. Here's how it works. The overhead wire carries high voltage electricity. The pantograph makes contact with the wire, power flows into the train. Inside the train, equipment called a transformer changes the voltage, then it goes to a converter that controls the power. Then the electricity goes to the traction motors. Motors spin the wheels, so overhead wire gives pantograph, gives transformer, gives converter, gives traction motors, gives wheels. That's the full chain. And yes, this happens in milliseconds, constantly adjusting while the train moves. Visual. Overhead wire gives pantograph touching, gives arrows showing power flow into train, gives transformer block, gives traction motors. Now here's a very UK specific thing, the third rail system. In many areas around London and the southeast, trains don't use overhead wires. They use an electrified rail next to the track called the third rail. The train picks up electricity using a shoe that slides along that rail. The process is similar. Electricity flows through the third rail. The train's shoe collects it. Power goes into electrical equipment. That power feeds the traction motors. Motors turn the wheels, so overhead power uses a pantograph. Third rail power uses a pickup shoe. Why does the UK still use third rail in many places? Because it was easier and cheaper to build in older rail areas, especially with bridges and tunnels. But it has downsides. Safety risk, exposed electrified rail, weather issues, ice and debris, limits on power compared to overhead systems. So the UK is slowly moving toward overhead electrification in many areas. Visual third rail track view gives pickup shoe, sliding gives electricity, arrows gives motor. So now you understand something important. A modern electric train doesn't need a front engine. It just needs a way to collect electricity. Equipment to control it, traction motors to move the wheels. That's why many modern trains are called multiple units, meaning the power is built into the train itself, not a separate locomotive pulling coaches. Now let's go to diesel trains, because diesel trains are interesting, and most people misunderstand them. In non-electrified areas of the UK, trains often run on diesel. These are usually called DMUS, diesel multiple units. And here's the key point. Many diesel trains do not directly drive the wheels mechanically like a car. Instead, diesel trains often work like this. A diesel engine runs inside the train, usually under the floor. That engine turns a generator, or the generator produces electricity. That electricity powers traction motors. Traction motors turn the wheels. So diesel gives generator, gives electric motors, gives wheels. This is called diesel-electric power, and it's extremely common in modern rail. Why do trains do this instead of mechanical drive? Because mechanical gear systems for trains become heavy, complex, and inefficient at large scale. Electric motors are smoother and easier to control, especially when multiple carriages need power. Some DMUs use a more mechanical system, but diesel-electric logic is the best way to understand modern traction. Visual underfloor diesel engine gives generator, gives electric line, gives traction motor, gives wheels. Now let's answer the question from the beginning. Why do many UK trains look like they have no engine? Because modern passenger trains often spread traction equipment across multiple carriages. Instead of one huge engine pulling everything the train can have, motors on several bogies power equipment in different cars. Better traction and acceleration. This gives several advantages. Faster acceleration, better performance on hills, more reliable. One motor failure doesn't stop the whole train. Better weight distribution. No need to turn a locomotive around. That's why modern UK trains often have a driver cab at BOTH ends. You don't need to rotate the train. The driver just walks to the other end and goes back. Next question. If trains don't have steering wheels, how does a driver control them? Trains don't steer left or right. The track decides the direction. The driver's job is to control power, acceleration, braking, safety systems, speed limits. So instead of steering, train drivers use power handle, throttle, or brake handle, safety acknowledgement systems. Modern trains also use systems like AWS, automatic warning system, TPWS, train protection and warning system. These systems help prevent a train from passing signals dangerously. So the driver is not steering, he's managing speed and safety while the rails handle direction. Now braking is where trains feel scary because they're so heavy. Train brakes are designed with one main rule: they must fail safely. That means if something goes wrong, the train should stop, not accelerate. Most modern trains use air brakes. The system maintains air pressure. The driver reduces pressure to apply brakes. If the system loses pressure suddenly, brakes automatically apply. That's why emergency brake systems are so effective. They basically force the braking system into maximum stop mode. But here's the truth people don't expect. Emergency brake does not stop instantly. A fast train still needs distance to stop, sometimes over a kilometer depending on speed. So emergency brake is powerful, but not magic. Here's something modern electric trains can do that cars can't do as efficiently. Regenerative braking. When an electric train slows down, the traction motors can work in reverse. Instead of consuming electricity, they generate electricity. So it becomes wheels turning, gives motors generating electricity, gives power, goes back to the system. This saves energy, reduces brake wear, and makes trains efficient. Not all UK rail systems can always send energy back to the grid, but regen braking still improves efficiency inside the train. Let's summarize everything you learned. A UK train moves because of traction motors. Power comes from either electric train overhead wire. Third rail gives collection system, gives power control, gives traction motors, gives wheels. Diesel train, common DMU. Diesel engine gives generator, gives electricity, gives traction motors, gives wheels. And modern trains spread these motors across multiple carriages for better performance. So next time you ride a UK train and you can't find the engine, you'll know exactly what's happening under your feet. If you want, I can make a part 2 where I explain why steel wheels work on steel rails, why trains don't slip easily, how signals control traffic like air control towers. If you enjoyed this breakdown, subscribe for more UK transport and technology videos and comment below: overhead, electric, or third rail, what's better?